exponent rules. All right, so we're going to look at this particular topic. We're going to look at using something called definitions and proofs. Okay, so I'm going to start out with this. The definition of an exponent. The definition of an exponent is this. X to the n power equals x times x times x n times. So this is a really logical way of explaining what an exponent is. Now, we can add something to this definition, but I'm not really going to do that now. This is true for real numbers, right? This is true for real numbers, except what real numbers wouldn't this work for? Can you guys think of a number that this rule wouldn't work for? Yeah, like negatives, we can't do that, right? So it's really only true for non-negative numbers, right? Can anyone think of a number that's not negative that this still wouldn't work for? 0. It doesn't work for 0. We can't multiply x times itself 0 times. So it's really only true for positive numbers. Can anyone think of a positive number that this wouldn't work for? Okay, a fraction gets kind of complicated.
But also 1.
Does this work for 1? Let's try it. So if we had x to the 1, that would equal x times itself 1 time. So it does technically work for 1, right? What if the x is the 1? Does it work if x is 1? 1 to the n power would be 1 times 1 n times.
So it would technically work.
So technically it works. Right, but really if we were to think about this, like 1 to any power is just going to be 1. So we would call that like I don't know if you would call that necessarily an identity property. 1 is the multiplicative identity in that case. So it sort of is related to the identity property. But we could call that like an axiom, a lemma. It's like a little thing that we proved off of our definition. So we showed that, well, for 1 to any power is just 1. Right? But the definition technically does still work for that. Now, like I said, fractions. And that's a good question. Like, does this really work for fractions? We're not really going to look at fractions today. So let's just say that it doesn't really work for fractions. So in that case, this really only works for positive whole numbers, right? It only really works for the natural numbers. 1, 2, 3, 4, 5. And if we think about it that way.
Wait, no, because the reason it won't work for fractions, because like I just put like 1/2, like 1/2 times a half. It's half.
Okay, so x could be a fraction.
Yeah.
But
X times
if n is a fraction, it gets a little bit complicated.
yeah, because it's a multiplied by a fraction of x.
So x could totally be a fraction, but then if n is a fraction, it gets a little more complicated. Interesting.
If you had perfect fractions, like if you had 2 and 1/2, then it would work. Like, yeah, have perfect.
If this is 1/2,
Yeah, n is 1/2 and x is like 2 or 4, then it would work. But
it actually doesn't. It doesn't work the way that you think it does.
Yeah, how would it?
So, 4 to the 1/2 power is actually the same thing as the square root of 4.
Oh, so it's 2.
So that would be 2. Well, like 2 to the 1/2 power is just the square root of 2.
So just choose the half.
Yeah, a square root is a half power. But again, so we're not really going to get into this. So we can say that this works. X could really be any number. But n really has to, for us right now, really has to be a positive whole number. In other words, what we call, in math, they call those the natural numbers, or the counting numbers. N would have to be 1, 2, 3, 4, 5, all the way up to infinity. Okay, so that's the definition of an exponent. Let's look at a couple things that get a little bit tricky with exponents. The first one is this. If I have negative 2 squared, that equals negative 4. But that's different than this. Negative 2 squared, which equals positive 4. Here's why. The exponent only applies to the number that is its base. Okay, so what this says right here, if we use our definition, this says negative, and then it says 2 squared. So it's 2 times 2.
Oh, so you just put a negative at the end?
Right, but this says, according to our definition, negative 2 times negative 2, which becomes a positive. So if the negative is inside of your parentheses, it gets repeated each time you multiply. If the negative's outside of your parentheses, or if you don't have parentheses, the negative just kind of sits there. Does that make sense?
Yeah.
So then, what if we had something like this? Negative 2 to the third power. Or negative 2 to the third power. Well, this one, again, we just see a negative and we say, okay, I'm going to leave that negative there, and then I'm going to do 2 times 2 times 2. So 2, 4, 8. Okay, negative 8. This one I have to do negative 2 times negative 2 times negative 2. Well, it's still going to be 8, but is it positive or negative?
Negative.
Yeah, because we have a negative times a negative, making a positive, and then a negative.
Every time it's an odd number, you would do a negative, and every time it's a negative.
Nice. If I have an odd number here, my answer will be negative. If I have a positive number here, an even number here, my answer will be positive. Okay? All right. So using our definition, we're going to do something called a proof. We're going to prove this theorem. Okay? A theorem in math is a rule, like a definition is a rule, but it's a rule that we actually have to prove is true. So a definition is just something that all mathematicians have kind of decided, well, this is what an exponent is. This is just what an exponent means. There's not really a proof to that. But a theorem says, well, if this is what an exponent is, then we can show that this rule will also be true. And here's the theorem I want you to prove, or that we're going to prove together. X to the n times x to the m would be equal to x to the n plus m. So before we prove this, an example of that would be something like this. 2 to the third power times 2 to the fifth power would be equal to 2 to the eighth power. And what you'll notice with exponents, a lot of the time now, I'm not going to actually write out, you could put this into a calculator and get a number, but a lot of the time I'm not going to do that. I'm just going to say 2 to the 8th. That's my simplified form. Okay? So how might we prove this? Well, here's how we do a proof. We start with one side of our equation, and we use what we already know to try to get this other side of the equation. So I'm going to say this, x to the n times x to the m. What does that equal? Remember, we can't use, the only thing we can use is the definition of an exponent. So the definition of an exponent would say that this equals what? X to the n would be x times x times x. How many times? N times.
Yeah, it'd be x times m times.
Times x times x m times. Now in a proof what we'll often say is, well, how do we know that that equals that? And the way that we know it is this is called the definition of exponents. So now is there something that we could say this equals? X times x n times x times x m times.
X times x n plus n times?
Yeah, brilliant. Doesn't this just equal x times x n plus m times? That's just counting, right? If I have n here and m here and they're all multiplied together, I just have n plus m.
Wait, are the base values not going to change?
Right, as long as we have the same base, right?
Oh, okay.
So if I had like x to the n and y to the m, there's nothing you can do with that. But as long as you have the same exact base, you can combine. Really good point. So, I mean, we could try to go into exactly how we know this, but I'm just going to call it counting. Okay? We can just count. Oh, I have n here and I have m here, so I have n plus m total. Okay. Now, what does this equal? Remember, we want to try to show that this equals this. Yeah, this right here equals x to the n plus m. Why?
Because they're both the same. Like,
what rule did we just use to get from this to
it's
this?
x to itself, like, and if n is like 2 and m is like 3, we just add it together as 5, so it's the same thing.
But what rule is this that says these two are equal?
The definition.
That's the definition of an exponent. So, this is often the last thing you'll do in a proof. I'm going to do it up here. This, the thing that we started with, equals this. And the reason is because if this equals this, and this equals this, and this equals this, then this has to equal this. And there is a name for that. It's called the transitive property. Transitive property. Like, think of transportation, right? Or transport. We can transport this down here. Equality says if 1 plus 1 equals 2, right? And 2 also equals 3 minus 1, then 1 plus 1 equals 3 minus 1. Equality, like if something equals something, it's also equal to everything else that's equal to that thing. Which sounds really complicated, but it actually just means that if this equals this, and this equals this, and this equals this, then this equals that. That's a transitive property. And so this was our theorem, and often they'll end a proof with 3 letters, QED, which stands for something in Latin. It's like quod est demonstratum, or something similar to that, which basically means like, thus it is demonstrated. Okay. So we showed that this has to equal this using properties that we already knew. Well, except you didn't really know the transitive property. I just kind of told you about it. But it makes sense, right? I mean, the transitive property makes a lot of sense. It's like I showed that all these things are equal, so they're all equal. So what can we actually do with this theorem? Now let's do some example problems that we might.
We can do our homework.
Yeah, you can do your homework. You're going to be able to do your homework with that theorem. So for example, if I had something like this, 5 to the 10th times 5 to the 12th, how could I simplify that using my theorem?
Oh, 5 to the 22nd.
5 to the 22nd. Beautiful. That's it. I don't want you to tell me what 5 to the 22nd equals.
Wait, but if,
Right? You're going to need a really big calculator.
Also, that's
Yeah.
wait, but if you did those two numbers, 5 to the 10th and 5 to the 12th, that would equal 5 to the 22nd? Okay.
Yeah. If you actually type these in, it would all be equal. We could do that with like a silly example, an example that we know. Like 2 to the 2, we know that's 4, right? Times 2 to the 3, we know that's 8. 4 times 8 is what? 32, I think. So what we're saying then is 2 to the 5th. Is 2 to the 5th really 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32.
Whoa.
So they really are equal.
Wait, okay,
But we're not gonna, I really don't want you to worry about like, what does this actually mean? Okay, go ahead, what was your question?
Wait, so, I was just thinking, if you had like, this like really off topic, but if you had 12 to like the 3/4, would it be, like 12 to the, like the 4th root times 3?
No, it would be 12 to the 3 to the 4th root. I mean the 4th root of 12 to the 3.
Oh, the 4th root of 12 to the 3rd power? Ah,
Okay,
okay.
what about something like this? X to the 10, x to the negative 5.
Oh, wouldn't it be x to the 5?
That would just be x to the 5. Yeah.
Oh, I get it, because it's like minus.
Yeah. So technically we're doing this with a negative exponent, even though we haven't really talked about, wait,
But if
what is a
but
negative
in this
exponent?
situation it works.
But in this situation, this actually does work. And we'll talk about negative exponents tomorrow because they actually do have a meaning. Yeah. Well, tomorrow's Saturday. You guys are all going to be here, right?
No.
Oh yeah, I forgot.
All right. Y to the 5th times y to the 13th would be
Oh, it would be y to the 18th.
y to the 18th. How about this one? Negative 3 to the 5th times 3 to the 7th. What would that be?
Would it be negative? Yeah, because it's negative 3 to the 12.
That's it. Because the negative just sits out front.
Yeah.
Right? What if I had this though? Negative n to the 5th times negative n to the 6th. What would that be? Okay, would it just be that?
I think so.
No, it would be negative because it's an odd number.
Okay, it would be this or it would just be that. Right?
Wait, why?
Because a negative number, right, to an odd power
Oh,
is going to be negative. So we could say that, or we could say we know that that would equal the same thing as negative n to the 11th. Right? But if I had something like this, if I had something like negative x to the 4th times negative x to the 6th,
Oh, it would be positive 10.
that would be either this, negative x to the 10th, or x to the 10th. Because we know that the even number here cancels out that negative. A negative times a negative is a positive. So as long as we have an even number of multiplications, our answer's positive.
Wouldn't it just be easier to write it as just x to the 10th?
Yeah.
Wait, what if it was negative x times x?
Like this?
Yeah.
Yeah, how would we simplify that?
No, but with the exponents.
Oh, like this?
Yeah.
In parentheses or not?
No.
That's just like this one, right?
Oh wait, yeah.
So it would just be negative x to what power?
Oh,
X
to 11.
to the 11.
Oh, with parentheses when you it would be positive.
No, because there were never any parentheses.
No, but with parentheses.
Okay, if we had parentheses here, this is a really challenging one. I don't think there's one like this on your homework. No, but this is a really good question. So if we had something like this, what you'd have to do is figure out, oh, negative x to the 5th is going to be negative x to the 5th. Then x to the 6th. And then you could combine these into that.
Oh.
Okay?
Okay.
So if this is in parentheses, because technically right now, this is not the same base. This negative x is not the same as x. And I can only combine them when I have the same base. I have to have the same base to combine them.
Oh.
Right?
So just
So what would this be? 2 to the 5th times x to the 7th.
it would just be the same.
Yeah, there's nothing I can do with that. I don't have the same bases. So I would just keep it the same. 2 to the 5th, x to the 7th. I can put it
Okay,
dot.
so they have to have the same basis, no matter.
They have to have the same bases for us to use this rule. Okay, one last thing, which we technically didn't talk about, but I think you guys will catch on pretty quickly. What if I had this? 3 to the 6th times 3. 3 is 3 to what power?
1.
The first power, right?
Oh, so it'd be 3 to the 7th?
So that would be 3 to the 7th. What if I had this? X to the 5th times x.
X to the 6th.
What if I had this? Y times y to the 19th power.
Y to the 8th.
Y to the 20th. Alright. Okay, I think you guys are ready. Any other questions? Really good questions today.